Hello. In this video I want to give you a broad brushstroke of what you'll be learning in trigonometry. And of course that's partly just because you might be curious about what's coming up, but also to give you a framework so that as you're learning things and there's a lot of details, you'll know where to put them. You kind of know how they work together. Okay. So we begin a lot of times either with trig ratios or trig functions. In this case, I'm going to start with trig ratios, where essentially you're working with right triangles, and I call them freeform because they can be in any orientation. There's no standardization, as there will be with trig functions. So they're useful primarily for indirect measurement, and that means you want to measure something you can't directly touch or access for some reason. And the basis for this is really similar triangles. So two triangles are similar if they have the same angles. They can be completely different sizes. They'll have the same shape. It doesn't have to be they don't have to be right triangles, but they have to have the same angles. And what we know about similar triangles is that corresponding sides have the same ratios. So what that means then is I can use a small triangle, right, to basically give me information about a big triangle as long as they're similar. So we're going to assume the angles are the same. And if this is like little a, little b, and little c, and this is big A, big B, and big C, and I'm using right triangles, but they don't have to be. Then let's say I want to know about use A and B, and I can measure everything on the small triangle. So I'd say, well, A is to B, so this position, relatively speaking, is to this position, or this side, as large A is to large B. And then if I know three of them, so for example, because this is a small triangle, I can know this side and this side, the lengths. And I probably can know the length of this side, but I might not be able to know the length of that side. So suppose this was like a tree or something, or a building, and I'm looking at the height here. Well, I can get three of these, put in numbers, and I can find the fourth one. So why does that work? For what we're talking about? Well, for a specific angle, we can create as many right triangles that are similar as we want. It's an infinite thing, right? So that is incredibly powerful. And in one of the videos, let me show you. In this first video, similar triangles to trigonometric ratios, if you're interested in watching that, I go through this much more deeply and explain how we needed to standardize what you call the different sides so that we can tabulate these ratios, and it becomes a lot easier to use. So in that case, we can come up with so many different ways of setting up these ratios. We needed to cut down on that. So instead of, going through all the trouble of measuring a small triangle and then using it for the big triangle, we instead tabulated we named the sides and then named how you pick two sides, and that's how we came up with the different functions. There's 6 of them. Here we have 3 for the trig functions, and then basically we tabulated those ratios. So that at that point I could say, oh, it doesn't matter which triangle I'm on. If this is a 60-degree triangle, then I can say the tangent, which will end up being the ratio of the opposite to adjacent, right, is always going to be, so here's 60 degrees, here's tangent, it's always going to be 1.7321. So that doesn't matter whether I'm working on the smaller triangle or the biggest triangle. I no longer have to work with a smaller triangle as I did before and say, hey, I'm using this small triangle to tell me about this big triangle. I just use the ratios that are in those tables. All right, so that was a huge thing. But now, once you've understood a little bit about trig ratios and how to use them for indirect measurement, we really went and standardized this even more and moved to trig functions. So how did we do that? Well, what we said is, for any rotation, right, we're going to now move to this circle. For any rotation, start at 0 for the initial side. So let me draw you a circle here. And I'm going to superimpose an XY axis just so you can kind of see where we are. So this would be 0 degrees right here. Start at 0 degrees for the initial side, rotate to the terminal side, whatever rotation that is. At the point where the terminal side intersects the edge of the circle, drop a perpendicular line to the x-axis. All right, so let's do that. So let's say I rotate this much. So here's my initial side, and then here's my terminal side. And then let me get a different color. So where this terminal side meets the edge of the circle right there, drop a perpendicular line to the x-axis. There's my right angle. There's my right triangle. Okay. And then essentially what you're going to have is these lengths, right, are going to form coordinates, right, xy coordinates. This is the radius. And essentially you now have, you can do all your ratios. But what happens is, because we have this rule of dropping a perpendicular line to the x-axis, we create, of course, the reference right triangle that I showed you, and it standardizes the definitions of the 6 trigonometric ratios to functions. And so where you have opposite over hypotenuse, for example, for sine, when you look at this, this is always going to be your angle, the one that's between the terminal side and the initial side. So this is always going to be opposite. This is always going to be adjacent. And this is going to be your hypotenuse. But if you look at it, notice that as long as we follow that rule of always drop into the x-axis, what's going to happen is the opposite is always y, the adjacent is always x, and the hypotenuse is always the radius. Okay. So essentially you now have an alternate way of defining these 6 trig ratios as in terms of x, y, and r. Okay? And what we're saying here is this distance here is x, this distance here is y. So you have x comma y. Right? Now, the other thing that you'll also see is that really for every point on the circle, right, you could rotate that and you're now being able to say I can define something for every point on the circle. Now, this idea of standardizing for all the rotations by dropping to the perpendicular to the x-axis creates its own set of rules, things like reference angles and so on. So let me give you an example of what would happen. Let's say I rotated a bunch and I rotated all the way over here. So what happens is, this is still my initial side, this is my terminal side, but obviously that's a rotation that's much greater than 180 degrees. So how do you come up with a triangle? Well, again, you follow this definition of dropping a perpendicular line to the x-axis. So from the terminal side here, where it meets the edge of the circle, drop a perpendicular to the x-axis. There's your right angle. There's your 90-degree angle, and the reference angle is the angle between now the x-axis and this terminal side. Okay, and that was actually true here, x-axis and terminal side. And what happens is you can figure out this difference. So let's say I rotated here 240 degrees. I know what the x-axis is, it's 180. The actual rotation here, this angle, right, is just the difference between 240 and 180, which will give me 60 degrees. So what happens is this 60-degree angle is really the same as what? If we extended this 60-degree angle, and therefore this 60-degree triangle has all the information that this one does. What do I mean by that? Well, the length of this side is the same as the length of this side. The length of this side is the same as the length of this side, and the radius, of course, is the same for both. I'm a little off because my drawing isn't perfect, but we know that's so. So then what that means is you don't have to do a lot of memorizing. If you just know information about all the right triangles from the first quadrant, you can use that to know everything about the rest of the circle, right? Or whatever right triangles would be the reference angles for everything else. So really, you don't have to memorize so much. What you really need to know is stuff about the first quadrant. And I say that because I've seen books present this sort of thing, where they give you a chart and they say, oh, you should know the signs, you know, plus or minus of all the trig functions and all that in whatever quadrants they're in. I'm like, why? Why bother? Just know, if you understand the real basics here, right here, these initial 6 trig ratios, all you got to do is draw yourself a picture and say, for whatever rotation, then drop down to the x-axis, and I know the opposite is always y, the adjacent is always x, and the hypotenuse is always r, so then you're really not memorizing, you're just restating these definitions. And then if what you can say is, well, if I'm on a unit circle where unit means 1, a measurement of 1 anything, 1 kilometer, 1 mile, a distance of 1 inch, then what happens is I can also allow the radius to be, I can use the unit circle. And I'll explain a little more why I can use the unit circle in general for all these ratios. But I can say, well, y over r can become y over 1 and just be y. So the sine, for example, is always y, the cosine is x, and then you've got all your other, definitions here. But so if I know that, when I look at my quadrants, what do I know here? In this first quadrant, I know that x is what? Positive, y is positive. Here in quadrant 2, x is negative, y is positive, right? In quadrant 3, they're both negative. And then finally in quadrant 4, x is positive, y is negative. And then all I have to know is, oh yeah, if I'm talking about y, I'm talking about sine. If I'm talking about x, I'm talking about cosine. And if I'm talking about tangent, just take the ratio y over x. So I don't really try to memorize anything. I just try to understand it, okay? Now, let's take a look here. Let me explain why I talked about the unit circle and said, well, I can really use the unit circle. And I'll clean this up a little, put a new sheet here. So what I'm going to do is I'm going to draw concentric circles, right? And it could be whatever radius. Let me go ahead and put the xy axis. And now let's talk about, for example, a 60-degree angle, right? So if this is 0, this is, let's say, 60. That's true for what? All the circles, right? It's the same angle. So then when you're talking about the ratios, wouldn't you agree? These are all similar triangles, right? These are all right angles. So the corresponding ratios are all going to be the same, right? So the ratio of this to this is the same thing as this to this, it's the same thing as this to this, so the tangents will all be the same. So that's why you can use just the unit circle. It's a lot easier. So then what we said was, okay, we can use the unit circle. It's going to make things a lot easier. Let's just know about, get some references so we kind of know where we are, some bearings. So if you look at a circle, you can immediately label things like this. Let's say let's assume the radius is 1. Well, this point here, all the end points, you'll obviously know because this would be what? Over 1, up none. Here you'd be over none, up 1, so on and so forth. -1, 0. And then over here, 0, -1. Right. All right, so already we've got 4. Let's get some other ones. What we do is we divided the circle into 8ths and 12ths to make it a little easier on ourselves. And basically we went by multiples of 30 or multiples of 45 degrees. And what happens is, why do we do that? Well, because if I know this, for example, 30-degree triangle, if I happen to know what the x and y coordinates are, I also know them for this one, don't I? If I assume this is 30 degrees. I also know them for which other one? This one here, this is also 30 degrees. I also know them for this one, although my drawing is terrible, I'm sorry about that. The principle is, hopefully the concept makes sense, is this length is the same as this one. This length is the same as that one. This length is the same as that one. So you're like, well, if I know 30, that means I also know what? 180 minus 30 or 150. I know 180 plus 30 or 210, right? And so on and so forth. I know this one, which is 330, which is 30 less than 360. So then how do I get to know what are these coordinates? Or the ones for 45, and so on and so forth. Well, I've got a video for you on deriving the coordinates. Yeah, let me see if I can find that. There. Hold on, I got a lot of pages flying around. Still flying around. Here it is. You can watch this video deriving the coordinates for the unit circle. All right. I'm going to do just one of them so you could kind of see. I'm going to do the 45-degree right triangle. So if we take, for example, a right triangle, because remember, we're only dealing with right triangles. As soon as wherever we rotate and drop down the perpendicular to the x-axis, we're creating a right triangle. So let's suppose this is 45 degrees. Well, if this is 45, we know that this must also be 45, right? Because it's got to be a total of 180 degrees for all three angles. And since they're the same measure of angle, that means that the sides, the lengths of the sides they form must also be the same. So if I let's say the hypotenuse be 1, and even though I don't know what this is, I'll call it t. But t must be the same length for both. And I can use the Pythagorean theorem, right, where we say a squared plus b squared equals c squared. So I'd have t squared plus t squared must be equal to 1 squared. So that's 2t squared equals 1. T squared equals a half. Now I take the square root of both sides. Technically, I have the absolute value of t is the square root of a half. And then t is plus or minus square root of a half. And although this is totally fine, most books like to rationalize this. They don't like a root in the denominator, so I'm going to multiply by square root 2 over square root 2. I'm multiplying by 1. And when you do, you're going to get plus or minus square root 2 over 2. So what that means is, at this 45 degrees, the right triangle that I would create would have an x-coordinate of square root 2 over 2 and a y-coordinate of square root 2 over 2. But that would be true of this one here, which would be at 135 degrees, right? 180 minus 45. The only difference is I have to compensate and say, well, it's the same lengths, but I'm in quadrant 2, so this is negative square root 2 over 2, and this is positive square root 2 over 2. So obviously, if you were here, you'd be at negative square root 2 over 2, negative square root 2 over 2, and so on and so forth. Well, by using the Pythagorean theorem, you can also find out very easily the 30 degrees and the 60 degree right triangles. So what that allows you to do, so if you watch this video, you can find that out. Okay, you can see how that's done. But that way we're able to create what's called the unit circle, right? Where you show the degrees and the coordinates and where everything falls. I haven't touched on yet the pies, right? You can also, the pi is just a different unit of measurement. So what happens is, once you understand why the positions are where they are, what they're representing, that a particular angle rotation is representing also a reference right triangle, and that these are the coordinates associated with the right triangle, you can also then branch out and say, well, okay, I'm going to learn about the radian. The radian is a different way of measuring rotation. So you have degrees, minutes, and seconds. Those are two ways of measuring rotation. Well, the radian is another way of measuring rotation. And again, it's not particularly difficult to understand, but I would say watch these two videos. Sorry. If you watch the meaning of pi and the definition of the radian, I think that'll make a lot more sense to you as to what the radian is. And what you'll find is that there's a conversion between the two, where basically 2 pi is equivalent to 360 degrees, which is 1 revolution. And using this conversion, you of course, this equivalency, you can convert from one system to another. But it also means you can start labeling the unit circle not only in degrees, but also in radians. Let's see if I can find this. So what we do is basically say, okay, if I have a whole circle, if I divide it in half and then in quarters, what I've just done is taken, for example, 1 revolution and divided it into 4 parts. Well, when we divide 360 by 4, we get 90 degrees, right? So that's how we go from 0 to 90 add another 90, 180, add another 90, because remember, a quadrant, a fourth, right, of rotation is 90 degrees, so add another 90, 270, add another 90, 360, right? You do the same thing with the radians. If this whole revolution is 2 pi, when I divide by 4, I get what? Pi over 2. So here's 90 degrees is the same as pi over 2. This is pi. This is 3 pi over 2, and this is 2 pi. But you can keep dividing, right? It's just however you keep dividing, you can get the rest. If you want to, let's say, divide by 12ths, so 360 divided by 12 is 30 degrees, so you'd have 30, 60, 90, 120, 150, 180, and so forth. You can do the same thing with 2 pi divided by 12, so you get pi over 6. So you get pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, and so on and so forth. Right? So that's how you get this unit circle. All right. Now, there's more to it than this. Through the definition of the radian, you're actually able to connect arc length and rotation, which is incredible. But again, what I want you to do is watch these 2 videos to understand that. That's a really deep concept. Now, what happens though is, because you can connect arc length and a rotation, what ends up happening is that then you have, every rotation you can now express in radians, which is connected to a distance also, and you basically have real numbers. And so now you're taking the trig functions of real numbers, and you can take a trig function of every real number. So you're really now talking about functions, right? So that's really, really huge. The other thing is, some of the times you'll have these oddities that will come up, like, because you know, for example, here the coordinates are 0, 1. If normally you wouldn't talk about a right triangle that's like this, right? I mean, you might have a right triangle that's like this, maybe really, really skinny and tall, but not like that. But now you can start talking about, well, what is, for example, the secant of 90 degrees, right? And the secant is r over x, right? So in this case, we'd have the unit circle, radius is 1, x is 0, and you're like, uh-oh, that's undefined, right? So you start getting into those kind of things, but you'll learn all that in terms of how to evaluate a function, right? So you go through all of that, and because you're evaluating functions, and so what I mean by that is, let's say here, let's take a look at our unit circle again. If I say I want to know what is the tangent of pi over 6, or of 30 degrees, let's stay there. If I say the tangent of 30 degrees, well, by definition, tangent is, oh, do I have that one? There's so many of them flying around. All right, well, it's x over r, I'm sorry, y over x, my apologies. And so you look at here and you say, well, y is a half, x is square root 3 over 2. So a half divided by square root 3 over 2. Take that ratio, and again, remember, it's just ratios that you're working with. Now flip and multiply 2 over square root 3. These cancel out. You get 1 over square root 3. So when you start, once you understand the unit circle, you can start evaluating the unit circle for different rotations for each of the 6 different trig functions. And when you do that, you can start creating graphs. So you run into, boy, I hope I don't run out of paper. I think I might. You start running into graphs. So for example, if I were to graph sine of the angle, what I can see is, let's see here, let's draw a circle. Since sine was defined as the y-coordinate, I'm basically looking at what are the y-coordinates of all these triangles that will be formed this way. So if this is a triangle, and this is a triangle, and this is a triangle, what I care about are the y-coordinates, right? So the y-coordinates, what do? They start at 0, right? Right here. Start at 0, and then they go up to what? 1. Then they come back down to 0, then they become negative, right? So they're up here, they're positive, but they're getting smaller as I rotate. So as I rotate, what's happening to the lengths They're getting smaller, and then they get to 0. Then they get to be, as I keep rotating, right, from 180 toward 270, they get negative, they get bigger negative, then they get less negative, and so on and so forth. So if you translate that, you have theta and you have sine of theta. What happens is, start out at 0, then you go up here, right, at their highest. Then they come back down, they're positive, come back down to 0 here. Then they become what? Negative. And then they become less negative, go to 0. And so on and so forth, but if you keep going around the circle, you keep generating this shape on and on. Why is that important? Well, we can model things that are what? Cyclical. Things that repeat over and over again, because this would be like on and on, right? So you'd have on and on, on and on. And how might that be helpful? Well, things that are repeated and cyclical, let's suppose I have some kind of sine function, and we're talking about temperature, and here's time, for example, and temperature throughout the day. And you may say, well, at what time here is the temperature a what? Max. Or maybe I want to know at what time is the temperature this much. Well, in that case, I start solving equations. So now I'm solving equations with trig functions. Okay. So that's a really big deal to solve equations. That's probably the hardest, I think, part of trig, I think. But that's fun, and you get to see how things are solved. Then we'll also talk about verifying identities. So identities are basically statements which are true for all inputs. So if I say there's an identity that's, for example, probably one of the most powerful identities, it's sine of an angle squared plus cosine of an angle squared is equal to 1. So it doesn't matter what angle I put in there. So if I say, for example, take our unit circle, suppose I work with 30 degrees. Well, remember the sine is the y coordinate, cosine is the x coordinate. So if I say a half squared plus square root 3 over 2 squared, is it equal to 1? So you'd have a fourth plus 3/4. Does that equal 1? Yes. And I promise you, if you try every angle possible, and it doesn't have to be just the angles that we see here, it could be anything in the middle, it's true for every input. So you verify identities. Now, why do you do that? Well, for one, it might help us solve some equations. There are some equations that would become a lot easier to solve if we could substitute. So for example, if I had the equation sine of an angle squared minus cosine of 2 times an angle equals negative a fourth, what I can do is, since I know this identity, right, sine squared plus cosine squared equals 1, basically I can solve for sine squared, move the cosine squared over here, and therefore I'll have 1 minus cosine of the angle squared. And then I substitute that in here. And finally, at least I'm now in what? The cosine, all cosine functions, which is a lot better than having 2 separate different functions like sine and cosine. Now I still have a single angle and double angle, and there's ways you can get around that using identities. But that's just to kind of show you why we would use identities. That's one big reason, is to solve certain equations. The other reason is you're going to be using, basically what you're changing is from one form to another so that you can perform an operation. That's what verifying identities is really the purpose of. So for example, if I asked you to add a half plus a third, the form it's in, you can't do it. But when you change the form, you say, oh, well, this is really what? 3/6. This is really what? 2/6. Now that I have a common denominator, I can say, oh, I can add them now. Now it's 5/6. Well, I was able to perform this operation because I was able to change from one form to another form. And that's what verifying identities do, can I change from one form to another, and now this other form is something I can actually work with. Okay, so that's another big part of trig. And let's see. This so far is all what I call, well, not what I call, it's just right triangle trigonometry. There is something you'll get into later where you'll learn about law of sines and law of cosines. You can use these on any triangle. So not just right. And you'll learn what those formulas are. I don't need to, give them to you right now. But that's what's really important. And really, most of the time, this is again used to indirectly measure things. So that's how we measure, like, how far is a star from us. We actually use law of sines and law of cosines to do that. Can't directly measure how far the star is, but we can do this. So that's incredibly important. And finally, you'll finish off with what we call polar coordinates. What we're used to is the grid form, X and Y. So if I have a particular point here, I say, oh, well, I go over, for example, if the coordinates you're familiar with are 3, 4, I go over 3 and up 4, and that's how I reach that point. Well, now with polar coordinates, you're talking about using the circle and rotation. What you could say is, well, how far do I have to rotate? And so that's, at least I'd be on this line, and then how far out do I have to go? So what I'm doing is superimposing a different system of reference, right? So you have concentric circles, right? And then you've got a certain rotation going out to it. So that's a different way of getting to that point or referencing that point. But now it's going to be with r theta. So how far do I rotate? And then how far do I extend out? On which circle am I? And so, for example, 3, 4 is going to be about 5 and 53 degrees. So if I rotate 53 degrees and go out a radius of 5, I will be at the same point as 3, 4. All right? So that's a really big overview of what you're going to learn. Hopefully that helps you with some framework as you're learning, so you know how things are connected to each other and how they'll be used. Thanks so much for listening.